Okay, this is math modeling in a different format. Since I've been told that I have a great face for radio, this should actually be better for you, I think. I want to start on page 58 of the notes and recap what we did with this example, where we had the energy consumption as a function of year. Its graph looked like this, and clearly the data is not linear. Some helpful person suggested that we try a power model of this form, and because of the properties of logarithms, remember, if we take the logarithm of both sides of our proposed model, it actually linearizes, and then we can apply graphical fit as we did last time to come up with a functional form and specific values of A and B, the parameters that best fit this data. But what if that helpful person who suggested the power form is not around? What if we are just looking at data ourselves and having to decide what type of model to fit? And furthermore, this is empirical modeling, so we're assuming we have no real background information on what form of model to choose. The data itself is going to drive our choice. So if that were the case, looking at this is clearly not linear, and I'll propose a couple of possible models. One is when you replace x by square root of x. The other is when you replace y by square root of y. So right now on the graph of the original data here, the year is being called x and the consumption is being called y. What would the graph look like if instead on the horizontal axis I put square root of x? So of course we could do that on Excel and find out, but maybe there's some intuition that we could come up with first. So first of all, for these small values of x, in particular, like there's an x equals 1. So what happens when I take the square root of 1? I get something that's pretty close to 1. And when I take something that's like 2 and take the square root of 2, I get something that's not all that far from 2. But when I take something like 10 and take the square root of that, I get something that's considerably smaller. Under that, this point, realize, would move all the way back down here to just a little bigger than 3. And a value like 8, when I take the square root, would move to a value a little larger than 2. And of course, in between, a similar thing is happening. And what you would actually get is a trend where the data is even more steeply curved than the original. Let's try the other idea. What if we replaced y by the square root of y? So again, for these small values of y, these points wouldn't move very much. But a large value of y, like 1,000, would bring this point down to, a little over 30. And here's a value of y that would move less, but down here, value of y that would move down here. And what we would find is that this original graph, which is concave up, is getting straightened out a bit. Quite a bit, actually. And so the new shape of data may follow a line roughly like this. Both of these transformations changed the concavity of the data. The original graph was concave up. When I applied this first transformation, I got a graph that was even more concave up. Over here, the same original graph was concave up, and when I applied this transformation, I got a graph which perhaps is almost zero concavity, or linear. And so if we're trying to linearize, of course, we're trying to look for those types of transformations which take the concavity toward 0. So here is a helpful table that some person has built, and right here in the middle is the baseline of no change. Those are the original variables x and y. And then here are some possible transformations we could apply to the y variable, some possible transformations we could apply to the x variable. And we just did square root of x and found out actually that what that did was increase the concavity. By increase, by the way, I don't mean just make the number larger. In magnitude, I mean make the number larger. So if the graph is already concave up, it became more concave up. If the original graph had been concave down, then it would have gotten, the concavity would have gotten less negative, and that's approaching zero or approaching linearity. When we tried replacing y by the square root of y, remember we found out that I should point out probably that this graph goes with this transformation and this graph goes with this transformation, just for noting that in your notes. We found out that y replaced by square root of y decreased the concavity. And then, because these various alternatives to the functions grow at different rates, it turns out that they will, like if I go here, for example, the concavity will be increased. Y equals square root of x increases the concavity a little bit. Log of x would increase the cavity more. Negative 1 over square root of x even more, and so on. So this is a ladder, and if you want to increase the concavity, a trial and error approach would be just go up rung by rung by rung and watch the concavity change, and when it gets as close to linear as possible, then you stop going up. Or if you want to go the other direction, you can start going down and doing either replacing x by something like x squared or x cubed, or conversely replacing y by something like square root of y, log y, and so on. So it's a trial and error approach. And let's see that in action. On Learning Studio, there is a spreadsheet, section 4.6, Bluefish, graphical. And the complete spreadsheet is done, so you needn't worry about reproducing this, but let me just illustrate a little bit what is happening here. So that is this data set from the notes. Happens to be a data set defined over time, and it is the numbers of thousands of pounds of a particular species of fish harvested from the Chesapeake Bay. The first thing that I should probably do is recode the years. The years go from 1945 to 1990, and I think we commented in class last time that that's not a very good idea from a complexity point of view or from a numerical point of view. These large numbers invite round-off error and not making very good use of the scales on my graph and so on. So what I have done is replace the year by, looks like the number of half decades since 1940. So go out 5 years, that's 1 5-year step, 2 5-year steps, 3 5-year steps, and so on. And then I can replace these large numbers with something simple like 1 to 10. Here is the actual Y data, and if I want to take a look at what this looks like, insert a scatter chart and see that this is not linear, it's wildly nonlinear, and it is concave up, or in other words, the concavity is positive. If I wanted to linearize that, then I should be trying to decrease the concavity since it's now positive. And so I should be trying transformations like this, replacing x by x squared, x cubed, or y by square root of y log y, and so on. Now in the first tab, let me just show the result of a lot of work. Here's the scaled year and the actual y value. Here's my first shot at transformation, a transformation to linearize. I replace y by square root of y. So this column B has transformed into column C. And then I did a scatter plot of the x values, column A, versus the square root of y values in column C. Here it is. And compare to the original data. This graph is repeated here. So notice the original graph is sharply concave up. The transformed data now with x on the horizontal axis and square root of y on the vertical axis is still concave up, but less so. So that's confirmation we're going in the right direction. We probably just need to go farther. And so if I look at my ladder of transformations, the next rung would be to replace y by log of y and see what that did. So here's a column for log of y and a graph of x versus log of y. And the graph has again gotten less concave up. Now it's harder to tell whether it's concave up or down at all. It doesn't seem completely linear, but it's not clearly one direction of concavity versus the other. Let's try one more rung on the ladder to replace y by negative 1 over square root y. And by the way, the reason for this negative sign is just to avoid reflection over the axis. If you try it without the negative sign, you'll see. Or actually, I'm sorry, it does reflect over the axis, but it keeps the trend. It keeps an increasing graph increasing. So your eye doesn't have to play tricks with an increasing graph turning into a decreasing graph and so on. Here's that. The concavity has decreased still further. And if I went one more rung on the ladder, replacing y by minus 1 over y, now I have a graph that I would clearly label this as concave down. In other words, I've gone too far. My original data was concave up, now it's concave down. I'm trying to get zero concavity. So along the way, there must have been a best point, and that might be here with minus 1 over square root y versus x. There were some other choices as well to replace x by a higher power of x, like x squared or x cubed. And so let's try that instead. So in my spreadsheet, I've continued to build new columns. There's a column for x squared, x cubed, x to the fourth, and so on, and graphs that resulted from those. Here's y versus x squared. Again, that's less concave up than the original, but it still is concave up, so I'd want to go farther. Here's y versus x cubed, and y versus x to the fourth. And this graph is getting hard to read because many of the points are clustered here near the origin. But from the larger points, at least, it looks like the concavity is mostly gone, that this is not so badly nonlinear. So of the pictures that I've seen so far, maybe y versus x to the fourth is about where I want to be. So that picked my rung on the ladder. And then I could take the data corresponding to this value and have either do a graphical fit or have Excel do a least squares linear fit. I've done the latter, and Excel came back with this formula for my transformed data. Now remember, x was replaced by x to the fourth, so in fact this model for the original data is saying that y equals 0.2431 x to the fourth plus 1.145 and so on. So I've built a column for the predicted values back in the original variables with my x to the fourth model. I can't read this formula on the screen, but you can bring up this spreadsheet and look at them. There's the x to the fourth. So here are my predicted values. Here are my actual y values, and then I finally did a chart of both of them with the blue diamonds in blue and the predicted values in the pink squares, and we see that this is probably not too bad of a fit actually. Some of the points are even overlapping. Some of the predicted values are overlapping the actual values, so you can't see them. It's not a bad model, and here it is. The data, noticed, has guided our choice of the functional form as well as then the actual parameters involved. Okay, that's the story on using the ladder of transformations. And finally, I want to briefly mention something that's mostly of historical significance, but not entirely. And that is, before the days of computers, it would have been very painful to do what we just did. So if you think about computing all of those square roots and logarithms by hand or on a slide rule or something like that, people didn't want to do that very bad. And so they were creative and said, there's another way. Instead of transforming the data, how about I transform the world itself? That I rescale my ruler, so to speak. It's measuring the data. So here's a small data set, and if you were to do a graph of this original data, it's highly nonlinear. You see y growing much more rapidly than linear. And so people would have gone to this interesting looking sheet of graph paper. The x-axis, or horizontal axis, notice looks completely normal. And so on this, I could let this be x, and then let's see, I think I went 8 squares per unit. So if here is x equals 0, and 1, 2, 3, 4. But notice the y-scale looks different than graph paper you're probably used to seeing. Here's the first unit, and then we jump quite a bit to the second unit, then less so to the third, fourth, fifth, and so on, up until I get to 10, and then there's another big jump, and another count of 10, and then another big jump if the scale went on up. What's supposed to happen here is that we are graphing a log of y. Not quite sure that's what I want to say. In fact, it probably isn't. Let's just say that this is y, but it's being graphed on a nonlinear scale. And so let's just graph the original data. I will have a scale then just chosen. This I'll make be 10. Then this becomes 20 and 30 and so on. 50, 70. Here's 90, here's 100, and then here's 200, 300, and so on. So you see what's happening. The first band is going up by factors of steps of 10, and then I go up by steps of 100, and then I could go up by steps of 1,000, and so on. And so if I graph the data, see the first point, 1, 10, is falling right here, and then 2, 22 here, and then 360 is right in here, and then 4, 165 on the screen is about right in here. Oops, here. And so if you look at that, the data itself is not so badly nonlinear. In fact, it's pretty linear. I'm at a weird angle to draw here. And so that tells me that this scaled data somehow is linear. Well, then what was the original data? So this is a logarithmic scale, so this tells me then that ln of y is proportional to x, because I see this linear shape. And then if I undo the scaling on y, this tells me then that y itself is proportional to e to the x. So if I suspect or wonder if my original data is exponentially distributed or growing exponentially, if I graph the data on semi-log paper, where the original or the independent axis is regular and the dependent axis is logarithmic, if the original data is exponential, then the transformed data should graph linearly on semi-log paper. So that's a very neat idea. And semi-log paper, you could, if you need this, you can find semi-log paper on the internet and download it. There's also log paper for other types of transform pairs, depending on what form of your data you're trying to show. Very neat idea, not used nearly as much since we have computers, but still occasionally useful. There are situations, of course, where logarithms are useful. So if we want to measure amplitude of earthquakes, for example, the Richter scale is a logarithmic scale. And the reason is because the range of earthquakes goes over like 6 orders of magnitude or so, and so you don't want to have to graph things like 1 and 1 million on the same graph and everything in between. pH also in chemistry is a logarithmic scale, and so seismologists or chemists would occasionally show amplitudes of earthquakes or pH on a semi-log scale like this. And that should do it. Thanks for listening.